Here we look at a gray code, and we're going to look at the gray code using N-cubes. The gray code is also called the reflective binary code or the single distance code. A gray code is a binary numeral system where two successive values are going to differ in only one bit, so in only one binary digit. This is also known as having a Hamming distance of 1. So that's again why it's called the single distance code as well. So if I looked at bit strings of length n equal to 1, I only have two choices because we are looking at a binary numeral system when we're doing this coding. So you're using our bit strings. So of length 1, I'm going to have just 0 and 1. So obviously they differ in only one bit. If I look at bit strings of length n equal to 2, what are your choices for these bit strings? Well, our usual order of writing these would be 0, 0, 0, 1, 1, 0, and 1, 1. However, with a 2-bit gray code, as you can see in this usual order, I do have change of just distance 1 between these two because there's only a change in that bit. But if I look at going from this bit string to this bit string, notice that you've had two changes. The 0 changed to a 1 and the 1 is changing to a 0. If I look at its neighbor there. So I cannot have this in a gray code. So what we do is we form a 2-bit gray code this way. This would be one way. And again, what's the reason that we look at this? Usually we put this order here because we're used to base 2. So we like to write our list as if it were, you know, the number 0 in base 2, the number 1 in base 2, the number 2 in base 2, the number 3 in base 2. So yes, that would be the usual order for us in base 2, but now we're not going to do that. We're just going to have a gray code. So this would be the equivalent gray code that we can use. And what we should think about with gray codes is just that we want this to differ in only one bit as I change from one vertex to an adjacent vertex. So that's why the cubes will come in handy to visualize this. So if I look at the address of each of these vertices for the 2-bit gray code, it forms a 2 cube. So what you have here is you have the address of this vertex would be 0, 0 bit string, then I can go to 0, 1, then 1, 1 over here. And so, you know, it's almost like when you were graphing with X and Y coordinates, you're just labeling them. But what happens here is I notice that if I go from one vertex to the next vertex to its adjacent vertex, like from 0, 0 to 0, 1, there's only one change in a bit. Okay, but I also had that down here. There wasn't a problem in the usual order. But now by rearranging this, you can see that going from 0, 1 over to 1, 1, its adjacent vertex, I do have just one change in a bit. So this 0 here is changed to a 1 here, and that's just one change in a bit, so distance 1. So there's a distance 1 between any adjacent vertex as you go around this cube in any direction here. So the adjacent vertices are now listed in a sequence, and that is called our 2-bit gray code. And if I want to put commas here, that might help you see that that's a sequence that I've listed. And that's not the only one. I could have, maybe I wanted to start with 1, 1. So if you wanted to do a gray code, you could do 1, 1 for the 2-bit gray code. And then what would be something, maybe you decide I want to change the 1 here to a 0, but leave the first one alone. That's fine. And then from there, to get all the possibilities, then I would probably say maybe change the 1 to a 0, since I already had a 1, 1. And then what's the other one I haven't used yet is 0, 1, the 0, 1 bit string. That would also be a possible gray code sequence. You just have to have Hamming distance 1. So notice that the gray code is also going to be called the reflected binary code. So where does it get that name for reflected? We have seen where it gets the name for single distance code. Now for the reflected binary code. To get the 2-bit gray code, we can start with listing the 1-bit code. So this would be the same kind of idea as you go up in more bit codes. But let's just start with a 1-bit code. It was just 0 or 1 are our choices, right? So you just do the choices. So it would be a 0 or 1. That's the 1-bit gray code. But now what we do is we follow it with a reflected copy. So I'm just going to make this my mirror here, and I'm going to reflect this code over. So this 1 is going to appear first, and then the 0. Let me give myself some room here. So now at this point, we have to append a 0 before the first set of codes. We're going to put a 0 before the first set. That means the part to the left of my dashed line here. I'm going to put a 0. So remember, you're coming up with all the possible 2-bit strings in a particular order so that they have Hamming distance 1. Then what we'll have to do to get the rest of the possible 2-bit strings, append a 1 before that reflected set on the right-hand side. Okay, so that would be the correct order to give us a change in only 1 bit at a time, and this would be all the possible 2-bit strings. So this is called the 2-bit gray code. And as you notice, what is going to happen if you look at these N cubes is we have a Hamilton circuit that's going to be formed. So a Hamilton circuit, if you remember, is going to be where you visit every vertex one time and you close it up. So you have a cycle there. So using the one that we have here, if you looked at 0, 0, and then you went to 0, 1, 1, 1, 1, 0, and then you would close it back up at 0, 0, because really it just goes back to the start of the code that we still have a distance of 1, a Hamming distance of 1. But when we write our gray code, yes, we just write the combinations that are possible. So for a 2-bit gray code, I would have 2 to the second entries there. So I have listed all 4 possible 2-bit strings. Okay, so as I mentioned earlier, a 2-bit gray code could also be written differently. So let's look at what we could do. Now, if I did have this 2-bit gray code and I wanted to use the reflection property, all you would do is you would use the reflective set, but you would append 0s after the first set and append 1s after the reflected set. So I know I can do the same thing I did before if you want to use that reflection property. Okay, but the only thing is, now what would I do? After the first set, I'm going to put 0s after this time. And then append 1s after the reflected set. So maybe I should have given myself some room here. So now I'm going to append some 1s after. Okay, so you can see you can get your 2-bit gray code that way as well. Okay, so now the 3-bit gray code. The 3-bit gray code, here we make 2 copies of 2 cubes, and we attach a 0 to the front of each string on the first copy, and attach a 1 to the front of each on the second copy. So you're doing this reflection, but then you're going to draw edges. So again, I'm going to decide, instead of doing this reflective writing out the strings, let's draw the 3 cube. So how is that 3 cubed formed? What you do is you start, so you have to have somewhere to start here. So you're starting, I'm just copying what I have down here just to show you how it works. So you're starting with the 2 cube. So you would start with a 2 cube and you would put the address down for each of these vertices. Address is how we labeled them. So it was a 0, 0. Remember, we went up and we called this a 1, 0. Then over here we call this a 0, 1. And then over here we call this a, actually we call this one a 0, 1, 0, 1. And this one was a 1, 1. Okay, so I copy this down twice. So I'm going to copy this same 2 cube. I know they say cube, but it's really 2 square there. Okay, and then as you write down the address, like you did before. Okay, now here's the change. So the change is we're going to put down a 0 to the front of each string on the first copy. So that was like we were doing earlier when we were doing the reflecting it in the mirror. So the first copy, we're going to attach a 0 to the front. And then attach a 1 to the front of each string in the second copy. So in the second copy, we're going to attach a 1. And this will give us our new address for each of these. And then from there, what do? Then we draw our edges to connect so that we have adjacent vertices and that we can make our Hamilton circuit as well. Okay, so this is known as the 3 cube, and I've drawn it down here already, but that's how it's constructed. It's that reflective property, but just visualizing it in a cube. So now what you do is you can travel from address to address, so that means from one vertex to another vertex, adjacent of course. So as you're traveling along, say you want to start at 0, 0, you can come up with a gray code. Just go from one to the next, and you're only going to be changing 1 bit at a time as you do this. And as you look down here, I've written out where we've used each of those only one time. So I wasn't doing a good job when I was tracing this out. But if I do 0, 0, 0, then I go to 0, 0, 1. Then I can go to 0, 1, 1. And then 0, 1, 0. And then 1, 1, 0. And then 1, 1, 1. Then 1, 0, 1. And then 1, 0, 0. And have we traveled along or visited each of those vertices at least once? Yes. So that's called a Hamilton path, and then it would close back up, you know, to the beginning where you started, which was 0, 0, 0, to form a Hamilton circuit. So here is the 3-bit gray code, and remember all possible 3-bit strings would be 2 to the power 3, which means I need to have 8 in my sequence here. And we want to list this so it has a Hamming distance of 1 from 1 bit string to the next bit string. I just want to have 1 change in a bit at a time. So here is a 3-bit gray code. If I want to form it this way with the zeros on the top and change it in this manner. If we use the reflection idea, we can see how to generate this gray code in larger gray codes easily. So again, I've just listed that 3-bit gray code that I had earlier. Here I just had it listed horizontally. I now am just going to list it vertically to make this a little bit easier to see how I'm doing this reflection idea. So I know I had to have 8. You can always just start with the 1 bit. If you wanted to start with the 1 bit, we know we have 0 or 1 as your possibility. And then remember, if we wanted to get to the 2-bit, what we did is we reflected it. So we took the 0, 1 and we reflected it. So here's my mirror here, and then I just reflect that. And then we attached zeros to the front of the first set and 1s to the front of this set. So if I want to get to the 3-bit gray code, what I would do is I would actually take this 2-bit, reflect it, attach zeros to the front. So I mean, I could do that as well. So I'm going to reflect this whole thing. Then this one too. Then I'm going to attach zeros to the front and then 1s to the front. So that's one way that I can get to this 3-bit gray code that I've listed up here. Now, if you wanted to just have another way of looking at this, what I could do is I could, so you see how things are growing in powers of 2, I could start with the 0, 1, and then go to 1, 0, and I could just go out to 8, so I know I'm going to have 8 of these. So I do 0, 1, 1, 0, then I do 0, 1, 1, 0. So I just kind of remember that that's my pattern, 0, 1, 1, 0, 0, 1, 1, 0. And then from here, remember how that worked is this 0 is, powers of 2 each time. So I'm going to have 2 of these in front, and then for this 1, I'm going to have 2 of those ones in front. For this one, you're going to put 2 1s in front, and for this 0, you're going to put 2 0s in front. So this is just a little trick here, and then you're done with that side of the table. So what you, in that column, you move on to the next column here, and then you again just say for this 0, I'm going to count 2 0s in front. For this 0, I'm going to count 2 0s in front. This 0, I'm sorry, that's a 1. And this 1, and then you're at the end of the table, so you're going to be done. And as you notice, here, you're going to have zeros in front for 4 of them and 1s in front for the other 4, just like we had when we were doing our reflection earlier. Okay, so if I just use that same trick, let's do the 4-bit gray code. So I've listed the 4-bit gray code. How many possible bit strings are there? Well, it's going to be 2 to the 4th, so I know there's 16. And how should you order them? Well, this will be one way that we could do this. I could start by that same 0, 1, 1, 0. See, I know that's my pattern there, and I can do 0, 1, 1, 0, and just keep copying 0, 1, 1, 0, and I need to get 16 of those. Okay, so from there, I can do that same process I was doing earlier, if you can keep track. So this 0, I'm going to count 2 zeros going down. For this 1, count 2 1s going down. This 1, 2 1s going down. This 0, 2 zeros going down. This 0, 2 zeros going down. The 1, 2 1s going down. This 1, 2 1s going down. This 0, 2 zeros going down. Then you're at the end, so you don't have to worry about the rest of those that were in that column. You move on to this column, and you count for this 0 2 times, this 0 2 times, because in that reflection, everything was twice as big there, so this 1 and the number of bit strings are powers of 2. This 1 twice, write this 1 down twice, and then we're at the 0. Okay, that's 0 twice. This 0 goes twice. All right, and then from here, I mean, I knew that's what it's going to look like because you can see how it's being reflected. So it's not that I have to do, once I get to this point, I know how it's going to look as I'm going to have just 2 more of those zeros, and then I do my 1s. And you might even want to just work with having the zeros up here and matching them down here. And then you could fill in the middle. That's one way to do it. Okay, but let me just finish. So at this point, now I know what it's going to end up being because if I take the halfway point, so 1, 2, 3, 4, 5, 6, 7, 8, okay, I guess this is it right here. So if I look at this, I know I'm supposed to have zeros attached to the front everywhere and then 1s. Now if I did my pattern, I'll just show you. I would look at that 0 and then copy it down twice in front. This 0, copy it down twice in the column. This 0, copy it down twice. This 0, copy it down twice. Okay, see, then you're down to 1s. So you know you're going to have enough 1s to fill up the rest of this column. Okay, so that's just a little trick that we can use there. And you can see you have half of it starting with zeros, half of it starting ones, and then in the middle we worked it out so that we have that nice reflection property holding. So it is going to have a Hamming distance of 1 between any adjacent bit string that's listed down here.